If you haven't done so yet, please pause the video and try to answer this question before listening on. We have in this situation a charged particle that is fired perpendicularly into a magnetic field. And as it enters the field, it's going to move in a circular path with a particular radius, r. And it turns out that the value of that radius is equal to the mass times the velocity of the particle divided by the charge of the particle multiplied by the magnetic field strength. Now this question wants us to find the magnitude as well as the direction of the magnetic field. And of course, that means it's asking us to calculate B. And so we're going to solve this equation for B. And one way of doing that would be to place this r over a 1, and then we can cross multiply. So if we multiply the mv by 1, we would just get mv. And then if we multiply r by qb, we would get rqb. And then finally, to isolate the magnetic field B, we can divide both sides of this equation by rq. And then we can see that the magnetic field has a magnitude equal to mv over rq. Now, luckily, the question has given us all four of these known values. The only thing we have to be careful about is that the radius is given to us in centimeters. So we just have to take the 5 centimeters and multiply it by 10 to the minus 2 in order to convert it into meters. With that conversion, we can go ahead and plug in the known values. So here are all those known values. Notice that for the charge Q, we have simply plugged in the magnitude of the charge. In other words, we didn't plug in negative 1.9. We just plugged in positive 1.9. So whenever you use this equation, just make sure you're plugging in magnitudes, which means that you should never include any negative signs. We will talk about later what that negative sign actually means. But for now, we can pick up our calculator and plug this in. And when we do that, we get approximately 0.264, and then the standard unit of magnetic field is Tesla. So this is the correct answer for the magnitude of this magnetic field. Let's now talk about the direction. Now, often when we talk about the direction of the magnetic field, we use the so-called right-hand rule. But because this particle is negatively charged, we're actually going to use what I like to call the left-hand rule. So let's explain that. So here is a crude picture of a left hand. Remember that we're using our left hand because the charge is negative. If it were positive, we would be using the right hand. The thumb is supposed to point in the direction of the velocity of the charged particle. And in this case, we can see that the velocity is pointing straight up. Our 4 fingers would be pointing in the direction of the magnetic field. And in this drawing, we don't yet know the direction of the magnetic field, so we won't put it in yet. And then the palm would be pointing in the direction of the magnetic force. And so in this drawing, with the hand, we would point some arrows, which got a little bit cut off there, and we would label that the magnetic force. Now, hopefully we can see from this picture that as the charge moves into this region of magnetic field, it's being pushed to the right. And that's what's causing it to bend its trajectory and move in this circular fashion. So we know that the magnetic force is pointing this way. And so what we would do is take our left hand and we would hold it flat out. We would point our left thumb upward in the direction of the velocity. Our left palm would be pointing to the right because that's the direction of the magnetic force. And then if you do that correctly, your 4 fingers should be pointing into the computer screen. And so we could label the direction of the magnetic field with these little X's. X's represent a direction that is into the computer screen. And so we'll just put a few in here, although it would be filling this entire rectangular space. So, in short, the direction of the magnetic field will be into the page, or into the screen, if you prefer. And so this is the final answer to the question.